Anybody want to say a prayer for us? After that thermo, no one's in a praying mood. Please.
Our dear Heavenly Father, we're grateful for this wonderful day, and we're grateful that we can be here in transport to learn some material and understand the world around us a little better. And we ask you to bless us to be enlightened this morning and to be able to focus on the material that's being taught. And bless us to have a wonderful rest of the day, and that the election results will be favorable for the best outcome that thou seest for our country. And we say these things in the name of Jesus Christ. Amen.
Amen. I was wondering where you're going with that for a minute. I was like, oh. Okay, so
have you seen what's it called? Other Side of Heaven.
I have seen the other side.
And the guy at one point's like praying. He's like, we've been praying for a strong wind this direction, but maybe someone else is praying for a strong wind the other direction. So I'm going to pray for a good wind.
Cancel each other out.
Yeah.
There you go. Well, I'm just praying for a good football game on Saturday. That's what I want. Huh?
Friday.
Or Friday. There you go. Yeah. Okay, so we were doing similarity solutions to the transient fusion problem. So we started out and I said we're going to start solving some more complicated problems, getting into the math a little bit. And that was an important part of transport, sort of starting these case studies, but it involves getting in the weeds a little bit more. So we're going to try and highlight some of the similarities and the analogies. So if we have this equation in fluids, it's also an equation in heat transfer and mass transfer. And we wrote those down, right? And so we took a little time and set up the problem to get from the Navier-Stokes equation, where we had a flat plate that's just starting to move into a semi-infinite domain, right? So there's the one side is bounded, the other side's infinite, okay? And we're looking at the diffusion of momentum into that case, or in other words, we had this plate, and I said the profile was going to look something like this, right? Where we had fluid flow, like that, because the plate's moving, and over time, that is going to grow and push farther and farther into that infinite boundary. And so we did some dimensional analysis and found out that we had too many dimensionless groups if we assumed X and or Y and T were independent, right? And so we said we have to find some way to combine them. And so we postulated this form, and we used our scale of the diffusion time scale to justify that relationship between the length and the time scale to justify that. And then we went through then and took this relationship and plugged them back into these derivatives, did out the chain rule, okay? And we got to this equation last time. And the great thing about this is that we reduced partial differential equation, right, in Y and then in T, now to an ordinary differential equation in just eta, all right? And the boundary conditions we saw collapsed too. That made us feel happy, at least made me feel happy. I don't know how it made you feel. That always makes me feel happy when one of those goes away, okay, and it works out. So now we got to this point right here. Well, now we have an ordinary differential equation that we need to solve. Yes.
You made it sound like it doesn't always go away.
It doesn't. Well, it should if the method works, right? Otherwise, we've done something wrong, right? If we end up with this stray boundary condition. So there is a case, maybe we'll see how much we talk about when we talk about boundary layers, but you end up with boundary conditions that seem to have problems that don't seem to match anywhere. And it turns out that's indicative of what's called a singular perturbation in your problem. Maybe you talked about this. Did you talk about solving ODEs by series solutions in your ODEs class? Do you guys remember that? I think they usually cover it. And then the math people don't like it. They're like, oh, this is useless. Like it doesn't show us any of the structure of the whatever. And it turns out it's like the most useful way of solving ODEs ever, okay? Because basically you can solve any ODE. You just if anything that's nonlinear, you can just linearize it and find a solution. And it turns out that almost all hardcore theories in physics and engineering are based on series solutions of ODEs or PDEs. Anyway, that's like a little bit of an exaggeration, but not that much. So and when you do it in physics or engineering, we call it perturbation theory. And there's a little bit of twist on what they do in series solutions in your ODEs class, but not that much. And you may have, if you talked about that, they talk about regular series and then singular series. And if maybe we'll get a flavor of that when we talk about boundary layer theory. But anyway, that was a long rant on sometimes there are issues with boundary conditions. So, and those come up in those problems. Okay, so other questions. That was a great question, Andrew. Other questions about where we got to sort of help make sure we're here. All right, we're good. Okay, so now we want to solve this ODE. So okay, so when confronting an ODE, the very first thing I do is see if you can separate and integrate, right? That's the easiest. Okay, if it's not, then I look and see, is it one I know? Is it a second order differential equation with constant coefficients, which is like 90% of your ODEs class, right? Okay, I'm gonna write down sines and cosines. Yeah, Brian, did you have, okay. Don't twitch, no, I'm just joking. Sorry. I reacted too quick, okay? So in this case, we can separate and integrate this one, okay? It's a little bit tricky to see, but we only have derivatives here, so we can actually define a new variable just for the sake of integrating. And the book uses psi, so I will too, and just define psi as d phi deta. Okay, and then we take that and plug that into this case, and so we're going to have d psi d eta plus c eta divided by 2 psi equals 0. Okay, so this happens because I don't have like another phi term out here, right? So I can go ahead and plug that in, and then I can separate this guy, okay, and integrate it. So I move that over, and then I divide by psi. So I'm going to get a 1 over psi d psi. And on this side, I'm going to have a minus c eta over 2 d theta, if I'm not mistaken. Okay. So then I integrate both sides. Okay. And let's do that. So we have natural log psi is equal to minus c eta squared divided by 4, and then plus some, what do I use here? I'm going to call this k1 prime, okay, so plus some constant. And I exponentiate both sides. When I exponentiate, I'm going to e to the, I'm going to get this plus e to the k1 prime, right, inside the exponential. But if I have a sum, I can make that a product, right? And so I'm going to just change my coefficient and pull it out front. So I'm going to call this psi equals oh, and I said I was going to do it, and then I forgot to do it. I'm going to call that one k1, okay? And then I'm going to make this exponential minus c eta squared divided by 4. Okay, so that's the first integration. Now I can plug in this right here and integrate again. So now I have the phi eta is equal to k1 exponential minus c eta squared divided by 4. Move the eta over and integrate both sides. And I'm going to have phi is equal to, and then your book does this as a definite integral. We're allowed to do this if we want. I'm going to integrate this from 0 to infinity. That's basically just plugging in my boundary conditions as the definite integral of k1 exponential minus c eta squared divided by 4. Okay, and we leave it as that integral for now. Okay, and let's see, 0 to infinity. I lied. I don't want 0 to infinity. We're going to call this 0 to eta, And then I'm going to make this in here an eta bar. Okay, that's just a dummy variable that I'm integrating. So I'm not going to do infinity yet. I skipped a step. Okay. Is that right? No. I need to leave another constant. Yes, Andrew.
Am I correct in remembering from calculus that the integral of e to the x squared does not have definite or like an explicit solution?
Yeah, so e to the minus x squared, can't write it out. There's a function called an error function. So let's see, an error function, I was going to say this earlier, but we might as well say it now. Error function is equal to the integral from 0 to, right, because we've got x of e to the minus x prime squared dx prime. That's called an error function. Yeah, just a second. So, and this is just tabulated, just like a sine or a cosine, right? So you might think, well, I don't know what that means, but if you can do that and generate, accurate enough answer for you, just plug it into Python. So if you do numpy.erf, I think that's where it is, you'll get out something. Yes.
So I've never seen using the bars and the primes. All you're doing is you're just saying, I would normally have an x here, but because I'm integrating 2x, I'm just going to call this x prime. Is that what?
Yeah, so just to distinguish this variable from what I'm going to plug in here,
Okay.
right? So I'm going to integrate it from 0 to eta,
Uh-huh.
right? And so these get integrated out
I see.
when I substitute them in.
I'm not seeing where the K2 comes from, because you only did one integration so far.
I did an integral to get the K1 here, and then I did another integral to get this one.
But you haven't
Well, we
evaluated
haven't done
the
the
integral yet.
Uh,
Isn't it definite, so you don't need a? Okay.
I think I need it. Why do I need it? So even though this is a definite integral, and then I left.
Does it come from integrating the DC?
So like if I integrate both sides, right? All I did when I integrate by d eta here, right? I could say I'm going to integrate that plus a constant. You're okay with that? If I did this, you're okay, right?
Yeah.
Okay.
Although I would still be a little confused why you're writing the constant before you evaluate the integral.
Why I'm confused? So you don't like this either?
Well, I just think usually you write the constant after you've actually evaluated the integral. Maybe that's just a moot point, but
Have we already evaluated on the left side?
Certainly evaluate the left side, right?
yeah, that's true.
Yeah, I'm not sure why I have to. I don't know. I'm not following the confusion there. So let me see if I can. Sweating this sweater. Make a mistake. All right. What can I say about that primary? So when I integrate something, like we're thinking, I integrate x squared, I get x cubed over 3 plus a constant, right? The idea is that, I can take the derivative of this, and that constant goes away, right? So if I call this phi, if I take the derivative of that, am I making anything wrong? I don't think so, right? If I take the derivative of this piece, I think maybe you're worried. So if I integrate this from 0 to eta and I have a definite integral,
Normally we wouldn't have a constant.
then I wouldn't have any constant left over, right? But don't I need a constant?
Because of the left side.
Don't I mean, regardless of the left side, don't I can't just assume I go from 0 to eta. Because this isn't like I know a value here, right? This is a variable.
I can't remember. I feel like back when they taught us, I remember Dr. Fletcher, and he's just like, mathematicians
Don't
don't
stop it right there. Okay, because I've had this conversation with Tom. Okay, and I don't believe that he's right on it.
Okay, good.
Tom doesn't like indefinite intervals. He tells you to always use definite intervals, right? Yeah. Forget that. I'll go read about this a little more, and if this is a point of confusion.
I think
Like
it makes
indefinite
sense.
intervals are a thing, right? We're allowed to use them. But yeah,
Right. It makes sense why, to me now, why you have the constant, even though you haven't evaluated the second integral, like the right-hand side integral. That makes sense. What I feel like should happen is after you evaluate this second integral, is you could like get rid of the constants because you've got a definite one. But that's going back to what Dr. Fletcher is talking about side.
that you could say that one more time.
So the purpose of, according to Dr. Fletcher, of integrating with a definite integral is that you can get rid of the constant. And so if you evaluate a definite integral on one side of the equation, then I feel like you could express it.
So I think maybe the issue here is coming, maybe it's because I'm evaluating this at a variable.
Yeah,
right,
and
as opposed to a number.
I guess.
Okay. And so when I evaluate this here, right, I'm gonna end up with something at m, okay, or at eta rather, you know, and what else am I gonna have, you know, to evaluate there? Let me go think about it, and like, when I'm not standing in front of you and like thinking about a different problem, and I'll come back and we'll have a quick review of indefinite and definite intervals. So I'll make like a note of that. So I remember to do it. And on Friday, we'll spend 5 minutes going over, and then we'll see if the straw man argument of, because I actually don't, you know, don't want to throw him under the bus too much. But, so let's see. And definite. versus definite. Some of these things I kind of forget, and I play fast and loose. So don't worry about that detail when I did it. Okay, so where were we? So assuming I can do this, assuming I'm not wrong, right? Now we need to evaluate the boundary condition, or we need to evaluate the constants using the boundary conditions. Okay, so the first one we'll do 0. So phi at 0. So that's pretty easy, right? Because I'm going to put a 0 in that bound. So I'm going to go with 0 to 0 of all that stuff plus k2. Okay. Well, an integral from 0 to 0 is 0, right? So that guy goes away. And we said that phi at 0 is equal to 1. So I know that k2 has to equal 1. Okay. That's why I know there has to be a constant, because it's not 0. Okay. And then I can evaluate phi1. So that's going to be the integral from 0 to 1 of k1 exponential minus c eta squared pi by 4 d eta 4. Okay, and now we can, like k1's a constant, right? This has to equal, or not 1, excuse me, this is infinity. 1 is next time. Today, if we get to it. This has to be infinity. Okay, and that has to equal, mess that up. Oh, I forgot the plus 1. Plus 1, because we solved for K2. There we go. I was looking at it going, it's going to equal 0, and then I'm going to say K1 is 0, and then this is a real problem because K1 is definitely not 0. Okay, so I do this. Now I can subtract it over, right? So I move the minus sign over. If I want, I pull K1 out when I divide. Okay, so now I get that K1 is equal to minus the integral from 0 to infinity exponential minus c eta squared divided by 4 d eta. We'll put the bar over eta to the minus 1. Okay, and so it turns out that this integral we know. Okay, so this is a Gaussian, so this looks like a bell curve, like half of a bell curve. So if you remember from statistics, a Gaussian curve. So this is like this half of the curve. Okay, and as it goes to infinity, we can find that. All right, and so you can, I don't know how to like solve it using substitution or whatever. Okay, it's just, it's known, so it's tabulated, right? So if you look it up in a table, this will give you minus a root of c divided by pi. Okay. So you can kind of think this in like a bell curve, the width here is the variance, right? You remember that? And usually I think it's minus x squared divided by 2 sigma squared in a Gaussian. So the c and the 4 have to do with how wide that piece is. So that's why it comes out here up front. Okay, so we can put that all together. We get b is equal to 1 minus the square root of c divided by pi multiplied by 0 to eta integral of the exponential minus c eta squared divided by 4 d eta. Okay, so now there's one more thing to do. Okay, we picked we've had this constant floating around from the beginning. Right? We put it right there, and we said, what is it? Okay, and we can pick whatever constant we want to put in there. There's nothing special about it. It cancels out, right? So like at the end of the day, I'm writing this in terms of phi, and you notice I have this c times eta squared, okay? And so the c is gonna cancel out of that. And the c out here is a normalization, okay? So if I change how wide this is, then this is dividing it so that the integral, sort of has the same number, okay? And so whatever I pick for c is fine. So the easiest thing to pick for c is the one that makes my answer look the cleanest. So I just pick c equals 4, okay? So if I pick c equals 4, that makes my life easier because that looks simple. So I just pick c equals 4, okay? So sometimes, like when people do this derivation, they just write c equals 4 here. And then everyone else says, well, why do you pick C4, right? Like, why can you just do that, right? And it doesn't matter. Again, I could put 227 if I wanted. It would be dumb, but I could pick it, okay? But so then it becomes convention to pick C equals 4 because it makes this clean, right? So then I get phi is equal to 1 minus 2 divided by root pi, integral from 0 to eta exponential of minus eta bar squared d eta bar. Okay, and then I said this is the error function, right? If you look right here, the error function, then I lied about the error function. The error function also has a 2 over root pi. Not that one. So, okay, so that's why also we wanted to pick 4, okay, because this gives us the error function here. So our answer is equal to 1 minus the error function of eta. Okay, where we'll box the error function too, so we remember what it is. Okay, and it turns out that people are so lazy that they made up a new function for 1 minus the error function. And they call it the complementary error function. And so the answer is sometimes written as ERFC of eta. Okay, and what's the complementary error function? Well, ERFC of eta is equal to 1 minus ERF of eta. Okay, so it's just 1 minus that. And I don't know, I think the statisticians did it. Okay, that's my guess, is that the people that do statistics were like, oh, I can't be writing 1 minus all over the place. I'll put a C in there. Okay, that'll make my life easier. I don't know. I don't know why they decided to define that function. I'm still waiting for the Doug function or whatever. Yeah. Anyway, yeah, you guys can make that popular. Okay, so, and then in the end, if we want, we can plug back in we did the dimensional analysis or the non-dimensionalization, and we can plug back in the dimensional variables. Okay, so we can write this as Vx divided by V naught is equal to 1 minus, and then the error function. And then we can plug this guy in, right? Y divided by 2 square root of nu t. Sometimes people leave the 4. Okay, we can box that one too. And at the end, we get box happy, right? Start putting boxes around everything. It looks like. All right, so that's the solution to that guy. So questions about the math, and I'm going to make some comments about the solution. Let's see, like, okay, I'm trying Zach's underhand. He said I gotta underhand it. I was closer. I was better. It's definitely better.
You didn't look as cool though.
Oh, well, now I can't go back. I gotta go back. Oh, look as cool. I already have like problems looking cool, right? So it's not like high on my list. It's like I don't automatically.
Isn't that why they stopped throwing an underhand ball in the or in the NBA?
But people don't. Yeah, was it? Was that a Malcolm Gladwell or like a?
Yeah,
like one of these books, and it was like if they would just shoot underhand,
it's more
they'd be
reliable.
proud. It's basically proving the Book of Mormon that we're just too proud. It won't even do what'll make you more money. It makes you look stupid. I believe that. All right. Okay, so let's talk a little bit about what we just did. Think about it for a second, all right? So it turns out this is, these kinds of problems aren't just this one problem, okay? What we did is indicative of a class of problems. So let me just say a few things. So what did we just do? All right, so we found out that we could combine variables. There was this special variable, y over 2. Okay, and our problem got a lot easier, right, when we did that. We went from a problem we didn't know how to solve to a problem that we could solve pretty quickly, okay? And what was interesting, right, is we only had one independent variable. So if you think about the solution that we had, remember, I drew this up just a minute ago, I think. I had Vx, and this is y, right? And we said that when I started out with, something that looks like that pretty early on, right? And over time, this penetrates, deeper and deeper into the bulk of the fluid up there. So this is time here, okay? So if we make this same plot, but now we plot eta as opposed to y, we see something kind of interesting. Okay, so now I plot eta versus bx. Okay, turns out this is 1 right here. We get a curve like that, and that's it. All of these curves, when you scale them by 2 over nu t, collapse to 1 curve. Okay, so in some sense, every one of these curves is like the same in some way. Okay, and When this happens, when there's this shape of a curve that everything collapses to, we call this a self-similar solution. Okay, so there's something common about that. Okay, and the transformation that enables this, eta is equal to y over g of t. Okay, this is called a similarity transformation. Okay, so one way to solve these kinds of PDE problems is to use this kind of a transformation with the hope that the solution is self-similar. Okay, so why did it work? Well, it worked because we had an unbounded part of the domain. Okay, so we had one side where we had, the fluid flowing, but the other side we had nothing, right? And because we had that no other side, we didn't have a length scale, right, that we could sort of use to say what's going on, right? And so that when we don't, that's a key. So if you see a problem and it's in a semi-infinite or an infinite domain, okay, you can try the similarity transform, and that sometimes collapses the variables and makes it easy to do. Okay, so the key here was that it was an unbounded domain. Okay, so either infinite or semi-infinite. When I say infinite or semi-infinite, does that make sense what I'm saying there? Okay, so infinite would be unbounded on two sides. Semi-infinite would be unbounded on one. Okay. So if you think about it, if we went back and, if you remember our dimensional analysis, we went back and we had a certain number of variables, right? We had Vx, y, t, nu, v naught. Okay, so we had, our old dimensional analysis. We had these guys, Vx, y, t, nu, and then v naught. Okay, we had 5, right? We had 3 dimensions. We can only have 2 dimensionless groups. If we add another length scale, if we had a domain boundary L, right? This is 5 plus 1 now. Now we get an extra group. And so we can have t and y be separate in that case. Okay, so that's another way of justifying why it is that the key is this unbounded domain. Okay, so I'm going to write this. So this is the bounded length scale. We go from 2 groups to 3. Okay, yeah, Andrew.
I was gonna say back over here, where it collapsed from several curves to one. Is it correct to say that those are all like a linear combination of each other?
No, they're not a linear combination of each other, right? They're scaled. They're scaled by this piece, right? So when I say scaled, I mean divided by that part, right? So there's something about them the same, but they don't like all add up to be something, right? If I find the exact right thing to divide by, they all become the same curve. Okay. So there's something really deep actually about the fact that when there's no length scale, you end up with self-similar solutions. Turns out that in lots of places this ends up. In thermo, at a critical point, okay, there's no length scale anymore. And when it goes critical, all of the thing wants to phase separate immediately, and you get these fluctuations that don't have length scale, and they become self-similar. Okay, and fractals. Okay, I'm sure you've heard of fractals. Are self-similar objects. Okay, and so this was actually this connection between self-similarity and fractals was a really big insight, sort of in physics, in about 40 or 50 years ago, that they connected. And they connected this to the critical point in thermodynamics, and it connects to some deep concepts in physics. So this actually is like pretty cool, okay? Some of this stuff on like the depth of it. We don't have time to get into any of it, but it's actually, I don't know, it's fun, okay? It turns out in polymers, this matters a lot because you have a polymer, it's a random walk, okay, is at least one way to think about what a polymer looks like in solution, okay? And this also doesn't have a length scale when you want to look at the size of the polymer, okay, the radius of gyration, and how it scales with the number of molecules, okay? And so it turns out there's a constant that scales with that comes from that's called the fractal dimension of this polymer, okay? And it has to do with the self-similar solution that you can come out to solve for this, okay? So anyway, this is like, there's some deep stuff here, but it's kind of interesting, at least to see in this case with transport, okay? When there's no length scale, you look for something similar, okay? So there's one more sort of physical insight to add here, which is, can we say something about what this G means? Okay, so if you think about it, there's, like I said, this is sort of penetrating. There's a penetration depth that's going on. And what you've done when you've divided by G is you've divided out that penetration depth, okay? And you're sort of shifting everything back. So that G of T equals to 2 root nu T, okay? This is a penetration depth. Okay, or we also talk about it sometimes as a boundary layer. Okay, so this is how far, the momentum is diffusing in the solution. That's the length scale that's characterizing how far that's going. So there was no length scale inherent. This is the one that appears, right? And that's growing as a function of time, okay? So that's a boundary layer. I'm trying to think. So one way so if I take this solution, this is actually it should be the air function complement, right? If I'm not mistaken. If I want to know where, and this flip, I want to know where this starts to get pretty close to the axis, right? There's some point, this goes on, this is asymptotic, right? But there's some point where it gets really close. So at eta equals 2, this distance here is 0.005. Okay, so sometimes if you want to think about how far is my velocity penetrated, I can take 2 of that thing, okay? And a quick and dirty way to look at that is to just go to 2 eta, and 2 eta is equal to 2 times 2 root nu T, which is equal to 4 root nu T, okay? And that gives you a length scale, right? About how far into the solution my velocity is penetrated. Okay.
So you're saying that's
Zach, and then we'll have Andrew.
Eta is y over 2 square root nu T. Why did we, when we took 2 eta, why did we just take it 2 times G sub T? Oh, are we getting y from that? I see what we're doing.
We're getting Y. Yeah. Did you have another question, Andrew?
I was just asking, so that becomes our length scale is 2 eta, is what you're saying.
Yeah, I mean, like a length scale is kind of like a ethereal concept, right? Like in a way, this whole thing is a scale, right? So if I want to know where sort of it becomes, 99.5%, I can look at 2 of that. I could look at it at 1 of that. That would, it would tell me something different. So what you want to make as a scale, you can kind of pick. Is it a meter? Is it 2 meters? Fine, whatever, right? But okay. So it turns out that if we wanted, we could go back and solve this problem again without assuming this square root of nu T dependence. And I don't want to take the time to show how to do that, but it turns out that you can just plug in this G of T and turn the crank, and you end up getting a differential equation for G that you can solve, and it'll give you this other piece. Okay, so if that intrigues you, or if that's something that you need for homework or something that I didn't catch, I don't think it is, but if it is, let me know, and I'll go over that next time. Okay. So let's barring any questions, let me set up what we're gonna talk about tomorrow. Right, we got 5 minutes, and we can start ourselves on like the 28, 29, it's halfway, okay, which is separation of variables. Okay. So in this case, we used the similarity method when we had no upper boundary. Okay. What we're going to talk about on Friday is solving the case where I do have a boundary. So I'm going to have unsteady laminar flow between parallel plates. Okay, where this gap is B. Length B is what we're looking for. Okay, so we're not going to be able to use similarity anymore because now we have length scale, right, which is B. And so we're going to have to use a new type of solution method, which is called separation of variables. So I think you've probably heard of separation of variables, most of you. You may have done it. I don't know if Tommy does it in heat transfer. Does he do it in heat transfer? Do you do separation of variables? We did it in my heat transfer class back when Richard Rowley taught it. So I guess Tommy, if he didn't do it, he's not as hard as Dr. Rowley. You'll have to tell him I said that. Okay. But so it turns out that separation of variables has lots of steps. Okay. And there's some deep theory that I want to touch on a little bit. So what we're going to do is we're going to do an example first. Okay, so instead of like giving you a high level overview, which I think will just go, okay, and make everyone fall asleep, we're going to do this example on Friday. And it might take us even more than just Friday to do the example, because it took me like 9 pages of notes to just get it done. Okay, I did that really extra all the steps, because the first time I think you see separation of variables, if you haven't seen it before, you're like, it's confusing. Okay, but there's 5 big steps. We'll do the 5 big steps. We'll get our way through it. Then we're going to back up and think a little bit about separation of variables, kind of like how I talked about similarity a little bit, but we'll go into a little more depth of separation of variables, because it turns out that if there's one technique that you can kind of think of as PDEs of solving lots of problems, it's separation of variables. It's the most flexible solution technique for solving PDEs that I know of. Okay. So I think it's worth it to kind of step back and think about that a little bit, because it might come up in lots of different places. Okay, so that's what we're going to do. I think I'll just end right there for today. I just wanted to kind of give us that highlight. Okay, so we did this problem with, no boundary. We're going to do a problem with the boundary. And it turns out that just adding that one thing is going to give us a completely different method that we need to use to solve it. Okay? Yes.
Can you go over again the 0.005 and the 2eta equals the 4 square root nu t? When would we use those in combination? Like we're asked to give a 99.5%. Like,
Yeah, so like the thought would be like if you wanted to know like physically, if I said you had some flat plate, I give you a bunch of variables, you knew the viscosity, okay? And you wanted to know at some time t how far away from the surface of the plate that you've been moving,
like velocity stuff.
where the velocities were really starting, right? This would be, you would take 4 square root of nu t and you plug that in.
Okay.
Right? That would give you a length.
Okay.
Does that make sense?
Yeah. Yep.
Okay.